Good afternoon and welcome to the Jones Seminar. Today we're very fortunate to have a speaker.
I don't think we connect.
And some people are having a really good time, which I'm really happy about, but I would like to draw your attention down to the front of the room at this point. Thank you. We did have a speaker who was going to talk about robotic medicine, and I'm very apologetic that he had a family emergency and could not make it today. But one of our own faculty members has stepped into the breach and is going to tell us about what I think is an equally interesting topic. Ron Lasky is an instructional professor at Thayer School, where he's also director of the Cook Engineering Design Center, founder and director of Thayer's Six Sigma program. And his background is that he started out thinking he might be a military kind of guy and went to West Point. Decided after 3 months that there were better places for him. Transferred to Cornell, where he got his Bachelor of Engineering and PhD in Material Science. He also got a Master's of Science in Applied Math from SUNY Binghamton. He's a licensed professional engineer with over 30 years of experience in electronic and optoelectronic packaging and assembly at IBM, Universal Instruments, Cookson Electronics, and Indium Corporation. He's written or edited several textbooks. And today he's going to talk to us about the impact of environmental legislation on electronics manufacturing in Europe. Please welcome Ron Lasky.
Thank you. Everybody can hear me, right? So I'm going to talk about Rojas, the impact. And I would like to acknowledge, in about 2002, I started working with Indium Corporation. And actually, essentially, everything I'm going to show you today is a result of working with them. So I really have to give credit for them for most of this. And as you might guess by the name of the company, they were the first company to find a practical use for indium metal in the 1930s and continue to work in that business. But also in the probably late 70s, early 80s, they got into electronic materials, which is how I work with them, mostly in solders for electronic assembly. So what and why is Rojas? Well, Rojas stands for the Restriction of Hazardous Substances, and it's a European Union directive that was effective on 1 July 2006. And it restricts the amount of chrome-6, lead, mercury, and two flame retardants, PBDE and PBB, to less than 0.1%. And I'll talk a little later about how they measure that 0.1% because it's a little more restrictive than it sounds. And cadmium at less than 0.01%. Why was this enacted? It was essentially enacted to support the recycling law that exists in the European Union, which is called WEEE, the Waste of Electrical and Electronic Equipment. And this law essentially is striving toward near 100% recycling of electronics. So I want to talk a little bit about the electronics industry so you can get us sort of all on the same wavelength here. The electronics industry is the largest industry in the world at about $1.5 trillion right now. And you see this map by some of my friends at Prismark Corporation. We tend to think a lot of it as being in the Far East, which of course it is, but there's still a significant amount in North America, to a lesser degree in Europe. And you can see the amounts are growing all over, but the percentage is becoming more and more dominant in Asia. Here's a typical electronic system. I'm sure we're all familiar with this, but you may not have seen a cost breakdown. And I apologize for folks that have been some of my students. They've probably seen some of these slides before. But if you take a computer that cost about $1,000, this is the percent breakdown of the different components of it, things like connectors, and substrates is an industry term for circuit boards. The people that make integrated circuits get the most amount of the money, and surprisingly, the little tiny capacitors and resistors that you can hardly see, some of them there, account for about $40. Assembling it and testing, it's about $140. This is a business term, sales, general, and administration, and profit, about $16. Getting it to the Best Buy and all of that's about $14. Just a little bit left for R&D. But most of the R&D that we hear about is done by the IC guys, and that would be part of their part of it. And the folks at Indium like to remind their customers that only 50 cents of the computer is in the solder that holds it all together. Well, soldering is, I argue, and of course this is an opinion, a little bit tongue-in-cheek, that soldering is the second science, and it may be the third if you would argue that astronomy was likely a first science. But the making of metals, we see this is the axe of the Iceman, the copper axe. But soldering is more ancient to it's far more ancient to Caesar than Caesar is to us today. That's how long soldering has been around. And it was usually done to bond precious metals and copper. And one of the things, if you look at the Roman Empire, if you've ever been to Pompeii, even the middle-class houses had running water. But every one of the houses, the running water came in lead pipes. So they were probably slowly getting a little bit of lead poisoning. But soldering is essentially what we're going to be talking about. And I guess I didn't make this point. Although there were 6 substances banned by Rojas, the one that arguably affects the electronics industry the most is solder. And it's the thing that people have struggled with probably the most in Rojas, and so I'll be talking about a little bit more. One of the things about soldering is what I call the miracle of soldering, and I don't think I really thought much about it until I gave talks like this. And that is that what we're really doing when we assemble something in electronics is we're essentially bonding copper to copper. That's what we have to do. And if we didn't have solder, the melting temperature of copper is 10,085 degrees C. So soldering enables us to bond 2 pieces of copper together at less than about 235 degrees C, which is near the melting point of tin, tin being the base material for most solders. And we do it often in the presence of plastic. And that is a requirement. If we couldn't bond copper to copper in the presence of plastic, we wouldn't have an electronics industry. I'll show you some of the plastic packages that you've probably seen before. Well, one of the things that happens in soldering is at the melting temperature of solder, and this is again mostly activated by the tin, the solder forms an intermetallic to the tin, a tin-copper intermetallic that not only makes a mechanical bond but makes an electrical bond. And the intermetallic is a requirement, but if the solder is too hot or your soldering time is too long and the intermetallic gets too thick, it can cause problems, most commonly in actually fracturing. This is a schematic of what this would be an electronic package. Cut away here, there would be an integrated circuit back up here. Here's a lead that looks gray because it's usually tinned with some sort of material that wets much more rapidly to solder than copper does, but there'd be copper inside. And here's a copper land on a printed wiring board. And here's actually a picture of a real, here's the kind of hard to see here. Here's the copper land, this thin piece right here on the circuit board. Here's the solder joint, and here's the lead coming off of the electronic package. So this is actually what we're trying to achieve. This is essentially a brand new Texas Instruments board. Even as long as I've been in this industry, I marvel that all of this can be made for $112. That means they've got to be making all of it for something like $50 to be able to make a profit. You see multiple integrated circuits. This is a special type of package called a quad flat pack. Here's the leads that are being soldered. You see a lot of little passive components. These are either resistors or capacitors. This right here is probably a ball grid array package. You can't see the little leads because they're little balls and they go through the entire area. Another, this is called a small outline integrated circuit. But I like this package because it shows the dominant technology of the day, the technology that has enabled miniaturization of electronics, which is surface mount technology, mounting the components on the surface. But it has, it's what it's also called mixed technology. It's got a lot of surface mount technology, but these connectors are mounted with the older through-hole technology in which the leads go through the circuit board. And probably the main reason for that is for mechanical strength, because this will probably be put in some sort of enclosure. We'll be plugging things in and out of here, putting stresses on this, and if there was just mounted on the surface and not having the strength of the lead going through the board, it could fracture. So this is a very common technology, mixed technology, and I wanted to just very briefly talk about how this is done. So to make a board like we just saw, and this is a very schematic, I cut all of these out from images on the web, and it's not exactly to scale. This is something called a Stencil Printer. The L isn't showing there. And essentially there are places on here where we want to mount and assemble the components. and we have something, this isn't exactly the stencil, but it's got holes in it. We line them up with a stencil printer so that when we put solder paste on this and have a squeegee go across it, it puts a little deposit of solder paste right where we want it on the pads here. Then, when we have a circuit board that has a solder paste where we want it, that travels along to typically two types of robots that place components. This is called a chip shooter, I think an unfortunate name, because if you're in all of electronics, a chip is usually an integrated circuit. But here, to what chips mean are the little passive capacitors and resistors that if you actually count all of the components in your cell phone, 95% of them would be these little tiny capacitors and resistors. This places them probably about 3 times as fast as a machine gun. And then this machine is much slower but more precise to place the more complex components, such as this plastic quad flat pack, which has more delicate alignment requirements. This all goes through an oven that melts the solder. The board is flipped over. A little adhesive is put on spots where we want to put passives on the bottom. And it goes into a curing oven. It holds the passives on the bottom, and we flip it back over, and we put in through-hole components that are like these connectors that we talked about here. And then this goes through a wave soldering machine, which is the older technology, which actually has a wave of solder that comes up and hits the bottom of the board. And when we have through-hole leads, the solder will be attracted to that and will wick up and wet it and form a solder bond. And it will also solder the passives on. So this is the type of assembly line. There are probably about 35,000 of these in the world, and they're making the $1.5 trillion worth of electronics. So back to, now that we know a little bit about assembly, back to the European Union. So it's the late 1990s. Revolution has happened in electronics that we've all lived through, but we might not really have thought about in the light of the way the Europeans do. And that is there's just a tremendous amount of electronic waste compared to what there used to be. And the Europeans have limited space. They have limited landfills, and they want it to be proactive. Their environmental pollution and green issues get a lot more press than they do here because, again, of the limited amount of space they have for landfills and so forth. They're also highly taxed, and they worry about who's going to pay for things like recycling and also any environmental impacts from waste materials. So right around this time, the European Union legislators started thinking about a recycling law and did some studies on this. And again, all of us know this, but I think it's helpful to be reminded. In the 1960s, computers were used for 10 years. By 1998, the average was 4.3. I'm pretty sure on average it's less than that now. And in around 2000, when people were considering these laws, innovative products were used for less than 2 years. I tried to get a beautiful picture of the AM/FM radio that my mom and dad got when they were married in 1941 that they kept for 30 years. It was a piece of furniture. This one actually I think looks a little junky compared to the one they had. But it was a piece of furniture. It was beautiful. You kept it. It worked. And there wasn't really a technology, a disruptive technology to replace it for at least 20 years. And yet something like this is obsolete in 18 months or less. So when they studied this, they found that 90% of electronics, again, this is in the late 90s time frame, in Europe was disposed without any type of pretreatment. There are heavy metals in electronics. And so on their own, a number of countries started drafting legislation for recycling. And this is the kind of thing that is happening even today in recycling, is that these types of materials, like 50 to 80% of e-waste, is collected for recycling and is shipped to Asia, and violating the Basel Convention on Hazardous Materials. And I'll show you some pictures of this later. So the European Union has been quite proactive in this, and this is just showing some of the laws. They have a packaging directive, and by this type of packaging we mean the boxes and the containers that the things you buy come in. They had an automobile directive, and a little surprisingly in this case, they allow electronics in an automobile, and that wasn't rescinded. So you can still, I'm sorry, they allow lead in electronics in an automobile. They have a batteries directive, and so things like batteries and automobiles are covered separate from the laws I'm talking about, which is this WE law, the recycling law, and the Rojas law. The WE law was supposed to be effective in 2005, and I'll talk a little bit later why it didn't quite happen that early. But Rojas was enacted on 1 July 2006. So what kind of things are covered? Well, this is one of the things in working with Indium, I got to know quite a bit about this, and they sponsored me giving talks on this. And it boils down to almost everything, but there are some exemptions. And I should say, too, that these laws troubled a lot of people in the United States. A lot of people actually, I go to meetings, and I mean, there are people almost getting in fights, physical fights over this. But the more I studied it, I really felt, for the most part, the European Union was trying to be reasonable in that they exempted things from making this change away from leaded solder to lead-free solder, recognizing that there were reliability issues. They made these changes, and but they gave exemptions. Because medical equipment is very important, they gave medical equipment an exemption, and it still has an exemption, beyond the date when they originally thought the exemption would be applied to. And they gave monitoring and control instruments, anything that is a mission-critical type of a component. It's monitoring, maybe something in a nuclear power plant. And the reason being because the European Union knew, and they did query a lot of companies, mostly the bigger companies like Philips and Siemens and IBM and Hewlett-Packard. The European Union knew that long-term reliability had not been established yet for solders without lead in them, and they didn't want to cause any risk in that regard. So all of these things have to be recycled, but only the things in green were covered by Rojas. So these are still exempted. Reason I underlined infected, I was giving talks on this, and as I was still kind of learning, I was still giving talks, and somebody who works for a medical office or medical equipment company in the South said in a delightful Southern accent, I won't try to repeat it or mimic it, but he said, Dr. Ron, those of us that make medical equipment try not to make anything infected. What is this? This must be a typo. It must be injected. They mean like something injected in your body. And I did some research, and I found out, no, it wasn't infected. And the good news is, if you're working in a hospital and somebody with dengue fever exsanguinates, that means to throw up blood, all over a piece of medical equipment, you don't have to recycle it. You can burn it. That's the good news. That's what it meant. So how were things? So the European Union is enacting these laws, and a lot of people, probably not just in the United States, but around the world, are kind of upset about some of them, complaining and so forth. What was the status around 2005? And actually, I believe I gave a talk on this as a Jones speaker, probably in about 2004. So these were passed in 2002. Companies like Motorola, Hewlett-Packard, Apple, I would say the bigger companies, really pretty much accepted it. Probably they felt pretty good because companies like this were being queried by the European Union people that were enacting this. What is your opinion about the exemptions? What will the industry need more time to establish reliability? The National Center for Manufacturing Science, it did a lead-free study in the 90s even. NIST, a group called INEMI, the International Electronics Manufacturing Initiative. This is sort of a consortium of companies, have done a lot of studies starting in like the early 2000s. And the main concern among the people of the 6 substances was the lead in solders. And why I say was this short-sighted, because I'll actually show you that when it came close to July 1st, 2006, some of the companies were flat-footed on some of the other materials. I'll talk a little bit about that. Hundreds of millions of dollars were spent in R&D to study what solders could replace leaded solders. And I should say, to actually make the implementation from, so this is R&D, but to make all the processes swing over, people have estimated in the neighborhood of $30 to $50 billion. I think that even could be low, but as I would be out giving talks, maybe every 3 months, I would go to meeting, as early as March of 2006, I would go to a meeting put on by a nonprofit organization like the Surface Mount Technology Association or the IPC, Printed Circuit Board Association. There would be people in the audience from small companies that still hadn't heard of this yet. And 20, 30% of their business was in Europe. There was also a pushback. I mentioned that some people were unhappy with this. The argument was that, you know, people were saying, well, gee, if people are making us get lead out, lead must be a major contributor to, or electronics must be a major contributor to environmental lead. And the answer is no, it's not. It's less than 0.5%. Batteries, 4 million tons. Bullets, 200,000 tons. This is kind of fun to me because myself and a graduate student some years ago did a little technical estimating on this. The tire weights are about 100,000 tons. So a lot of people were saying, why are we taking the lead out of solders for electronics? It's so critical when it's only such a small percent of what goes into the environment. And so there will be a lot of discussion at meetings about this. People actually did experiments where they would essentially grind up a circuit board, put some dirt in with it, pour some water in and let it sit for a year and then measure the water to see if they could measure any amount of lead, and it wasn't very much. And so people were really trying to push back against the European Union. And we'll talk a little later why that this perspective is missing a key point. Once it happened in the European Union, it became a domino effect. There's something called, because they started it first, everybody calls the next country doing it, which was China, China Rojas. And then there was Korea Rojas. The United States hasn't done it yet. But in a sense, it's almost irrelevant because what has happened to most companies, you don't want to make 2 flavors of a cell phone. You don't want to make a leaded cell phone and a lead-free. You want to make 1 flavor, so you make it lead-free. Because if you want to sell in Europe, it's got to be lead-free. So even though we don't have laws in the United States restricting lead in electronics, it is to the point of all but vanishing. And there are some exceptions, and I'll talk about them in a little while. So lead-free solder selection. Well, about 80 years of reliability and process data exists in lead-free solder. So as soon as the electronics industry started being created, say in the maybe even teens and 20s, you know, early radios and whatever, it was pretty much tin lead solder that people used. They used usually a eutectic tin lead solder because it melts at the lowest point. And so when people came to the point where wanting to get a lead-free replacement, everybody hoped we could get one that would melt at about the same temperature of tin lead eutectic solder, which was 183 degrees C. Wet well, what that means is when you get it near copper, it flows onto the copper and forms the intermetallic very well, and have equal or better reliability in reliability tests to make sure the solder joints would be robust. So this surprises a lot of people. Hundreds of millions of dollars were spent. People studied tin bismuth solders. You can get tin bismuth solders that melt at a low temperature. Tin zinc melts at a low temperature. Tin indium melts at a low temperature. And one of the issues with using tin indium is 1/5 the amount of indium produced in the world is 1/5 the amount of gold produced in the world each year. And most of it goes in the material for your flat panel displays. Without indium tin oxide, at least in this state of technology, we would essentially not have flat panel displays. So there isn't enough indium to make solder for electronics. So the winner was tin, silver, copper. And this is, and I'm making a long story very brief. The one that's kind of settled down is close to eutectic. 96.5% tin, 3% silver, and 0.5% copper. But it melts at 217. That's 34 degrees higher than tin lead solder. And it doesn't wet quite as well. And the reliability, we've now got probably, in some cases you could argue, 7 or 8 years of reliability data. And it appears to be, in most cases, equal to tin lead solder. But we don't have that long-term reliability that you'd want in a satellite or in a military electronics. We just don't have the data yet. So one of the issues, this shows a pretty good example of it not wetting well. This is a top view of this is what's called, again, a passive component, a capacitor or resistor. This dimension here is probably, this looks like a little bigger one, 80 thousandths of an inch. So this is tin lead solder. And you're looking down, and you see the solder joint is here, and you see the solder is spread out on the pad completely. You can't see any copper color. But here, you can see the copper of the pad. It didn't completely come out and wet the pad. So that's a common thing with lead-free solder. This doesn't show as well the fact that this is a tin lead joint, very shiny. This is a little more mottled. I have a better picture here. This is a good lead-free solder joint. This is not cracking or anything. It's just the type of structure that lead-free solder has when it freezes. And so we had to develop in the industry a whole new set of inspection criteria for people that inspect solder joints, because it isn't shiny as a tin lead solder joint. Because it doesn't wet as well, it doesn't fill holes as well in through-hole soldering. And I'm not a very good artist, but I think I showed you that in through-hole you have something like this pin that is inserted in a hole in the circuit board. And I tried to show this as a hole in a circuit board so it would have a pin in it. The bottom of the hole goes through a wave of solder in wave soldering. And this barrel of this hole has copper in it. And the surface tension wicks it up, and it should fill the top and form a nice fillet on top here. And you can see that's not happened here. And so that's one of the issues in using lead-free solders. The higher temperature, probably of anything for a process person, in addition to the fact that it doesn't wet well, is the fact that the solder for lead-free solder melts at about 34 degrees higher. And in some cases, there are solders that people use that are a little cheaper that don't have silver that melt at 43 degrees higher. And so you're exposing the inside of a package which has a lot of plastic. I'll actually pass around. This is a good package. It has surface mount components. This is a plastic quad flat pack. This is a ball grit array package. And it has through-hole components, mostly the connectors needed for strength. So when you run your finger on the bottom here, you can feel the through holes. So this is and it's got the little passes. This is kind of a classic modern mixed assembly package. Your cell phone, though, probably doesn't use any through hole. But anyway, this is one of the ball grit array packages. The package has the little surface or the little balls all around the underside of the package. And one of the things you learn when you study polymers is that polymers are not hermetic. For those of you that have need of a nylon comb, I haven't used one in a few years. If you took your nylon comb and you put it in the Sahara Desert for 20 years and it weighed 30 grams, if you put it in the Amazon jungle for 6 months, it would probably weigh about 31 grams. It would actually gain about 3% by weight water. And so polymer materials, which almost all inexpensive, affordable electronic packages have injection molded plastics that encompass here's the integrated circuit. They will sorb water. Water will slowly get in here. And actually at some of the interfaces, if it's been exposed at a high humidity and gone through some temperature excursions like hot to cold, you can actually get potentially a little almost physical water precipitating in an interface like this. The temperatures of lead-free soldering are high enough that when they go through the reflow oven that melts the solder, you can literally have an explosion of steam, and it can actually blow the package apart like this one's been blown apart. And one of the reasons to see this is the vapor pressure of water is not linear with temperature. When we were assembling with tin lead solder, we might be in this range here, and then when we go to lead-free solder, we've got to go up to this range. And literally the vapor pressure of water, close to doubling. And so this is a big issue when you assemble some of the component packages. You actually have to keep them in a hermetic bag and take them out just right before you assemble them. If you leave them out on the shop floor and you're doing assembly in Singapore where it tends to be humid, they could sorb water vapor and fracture, as I showed you. So around 2005, I remember I was at a conference, I was in a meeting with one of the guys who's like the leader in how to get ready for this. This is 2005. He's written papers on it. He's done a lot of work to get his company ready. And I saw him in a meeting, I think it was October 2005. So he's got to be in pretty good shape. He's only got about 8 or 9 months left to go. And so I saw him, I said, how are things going? And he was all stressed and discouraged. He said, it's a fiasco. And I'm thinking, I knew he was working on lead-free solder qualifications and all this kind of stuff you do to make sure you've got a process down. I knew he had done all of that like a long time ago. And I said to him, what's the problem? And he said, screws. So what are you talking about, screws? He said, inexpensive screws are made from steel, and then they're plated with chrome 6. So if you go to someplace like Home Depot and you get screws, they're probably, the ones you can buy for if you buy enough of them, you get them for a couple pennies. They're probably plated with chrome 6 to protect them. It's very difficult in the United States, at least at this time, to get screws that weren't plated with chrome 6. Chrome 3, which is the alternative, is more expensive because it's a special order, but it also doesn't protect as well from corrosion. And so it was a big deal, actually. One of the things with a lot of companies that held them up was getting corrosion protective coatings on things like steel that didn't have chrome 6 in them. So July 1st, 2006 arrives, or a little bit before that. Let's say a little bit before that. One of the things people had to do is they had to register their products for recycling. And you had to demonstrate the European Union that in addition to obeying Rojas, you don't have any lead and all this kind of stuff, that you're recycling on average about 85% of your product. You have to demonstrate that as Hewlett-Packard, RIM, Apple, whatever. And so these companies are starting to pressure the European Union, tell us what we have to do. And they weren't getting an answer. And finally, this is something the European Union left up to the individual countries. Like if you sold products in Germany, you had to satisfy the Germans that you had a plan to recycle 85%. You had to satisfy the French, the Spanish, the English, and so forth. So this one company sent one of their professionals over to get registered in Germany, and she arrived at Munich, went to the building where you were supposed to take a seminar on how to do this. The room held 200 people, 600 people showed up. And one of the things that surprised a lot of people, even though the European Union's official language for the law is English, the companies are all implementing this in their own language. So there are about 30 European Union countries. A company like Apple would have to register the iPhone in each of the 30 different countries in the language of the country. So you had to do Estonian, Latvian, French, German, Spanish, all of those languages, Swedish, Norwegian, and so forth. And so companies sprung up that became expert in this. And I remember giving a talk right around this time and found out that there was one company that would do it for like $1,500 a country. One country was $5,000 and then any other was $1,500. And somebody asked if I thought that was a good buy. And I said, are you kidding? I mean, could you imagine doing that yourself? So that was a big confusing thing. The other thing was that the European Union's definition of what 1% meant was very, very difficult. Because you could argue if you cross-section a screw, this cross-section of a screw, somebody would say, it doesn't have 0.1% hexavalent chromium in it. If you take the mass of the screw, the hexavalent chromium is just a very thin coating on the top. If you take the mass of the screw and the mass of the coating's probably much less than 0.1%. But this is not what the European Union meant. If you could take any piece of material, you take literally the first atomic layer of the surface of the screw has to be less than 0.1% hexavalent chrome. So obviously you can't use hexavalent chrome. And this was the definition that they had that I got to be pretty good explaining to people, which was per homogeneous material. And there are people that would be so angry about this. Because if you actually think about it, the lead in my laptop could arguably be less than 0.1% of the weight of the laptop. But what they're saying is when you look at an individual little solder joint, anywhere on it, it has to be less than 0.1%, which obviously you need lead-free solder for. So everyone expected Rojas importation disasters on July 1st. I mean, I looked to that like most people did Y2K. I thought that everything was going to be stopped at the borders of all the countries because people didn't have this and that. Well, it ended up that the European Union, the only thing they asked of a country was that you declare that it was Rojas compliant or not. And in other words, you would go there, Bob would go there with one of his $1 million products he'd make, and he'd just stand at the border and say, I declare this is Rojas compliant. Now, eventually they started asking for documentation, but initially that's all they asked for. And so there were no issues. And one of the things we discovered, and I kind of chuckled after I saw this, is it's just like in the United States. The federal government passes a law that's something like the health care, and what they forget is you need an infrastructure of 500,000 people to implement it. There was no infrastructure at all. The European Union had no infrastructure or very little to implement this. It's just coming online now. So in a sense, they work with kind of a partnership with companies. And I think there have only been a few cases of companies being fined any appreciable amount. Up to today, there are still mostly they call themselves lead-free, not Rojas, renegades that are still trying to fight this, thinking that somehow that this law will be rescinded, which I don't think. Just so I know, are we supposed to finish at what time? Half past? Okay. So it was interesting, though, that some companies were very aggressive in selling lead-free and Rojas-compliant products. And it's because there was a benefit that was not recognized by many people. This is some leaded solder paste that's printed onto a copper coupon. So this would be like the copper in a pad that you'd solder to. And notice the little deposits of solder paste get closer and closer to one another. So this is what we're leaving. This is the thing that everybody's upset that we're leaving. This is leaded solder that we've worked with for almost a century. Here's what happens when you reflow it. That's not all good. It wets really well. That's what we're leaving. It wets really well. But that's not really good, all good, because you're getting short circuits. Here is what happens when you print with lead-free. Printing looks the same. And then when you reflow it, that happens. Well, Motorola latched onto this in about 2001 and sold their first cell phone. And I purposely like this slide because it shows how long that they've been assembling with lead-free solder. This is a 2001 era cell phone. It's amazing they've changed this much. But this was assembled with lead-free solder. The reason they implemented way early was because they could not make a modern design with this kind of solder. They wanted closer lead spacings, and the only way they could get that was lead-free solder. Now, admittedly, there's good things and bad things. It's harder to make it wet, so in some cases you might have a solder joint that doesn't wet quite as well as you'd like. You know, you're not getting as much wetting. But this enabled closer lead spacings, and if you ask people that make miniature electronics today, they would tell you they couldn't go back to leaded solder. They couldn't make the product in as small a size as we have today. And this is still not widely recognized. There are really not many European Union importation crises. Again, I almost get in trouble for saying this, but my sense is the European Union has worked with the manufacturers in trying to minimize the effects. Short-term reliability has really pretty much been established. We've now, it's been in force for almost 4 years. The sky never fell reliability-wise. Companies like Motorola and Apple and IBM have kept track of this, and people are reluctant to publish reliability data because they consider it a competitive advantage. But the people I know and trust, they tell me essentially they can see no difference between leaded and lead-free solders. So SAC 305, and this is the way you abbreviate. This is tin, silver, copper. 3.0 is the amount of silver, and 0.5, not seen, is the amount of copper. That's an industry-accepted standard. It's pretty much been used. But one of the things that's happened, and things are happening in electronics that are independent of the move to Rojas that have really dramatically affected electronics, and that is a tremendous continuation of miniaturization. And the fact that historically the type of testing that was done to show that electronics are good was thermal testing. In other words, if this is a circuit board and I turn this on and it's in a computer, and I think we all know how hot our laptops get, when you turn it on, the thermal coefficient expansion of these different materials is not the same. And so you'll get stretching and shrinking comparatively, and you'll put stresses on these solder joints. And eventually the turning on and off can cause a crack in a solder joint. And so the type of testing that's done is called thermal cycling. And usually it's very strong. Like something like the cell phone, they'll actually expose it to like minus 65 C to 100 C. They'll literally put it in something almost like liquid nitrogen, well, not liquid nitrogen, but dry ice temperature to boiling water, back and forth, to make sure that the thermal shock doesn't break any of the solder joints here. So some work was done by my colleague Jean-Paul Kleck, and I actually hope to invite him here to speak to 103 about how he does modeling for data of this type, but he couldn't make it. But anyway, this is taking out the data points. This is tin lead, and this is how many cycles to failure, and obviously good is in this direction. And this is the shear strain range. And typically thermal cycling is in the lower strain. And if you look, this is SAC, this is the lead-free solder. in the data up to this time, SAC actually does a little better than tin lead solder. So for the historical thermal cycling type of performance that we were all interested in, it was better. For people, because of cellular phones and iPods, more and more people were interested in testing at a higher shear strain range in something more like what people call drop testing. Because what is the biggest threat probably to our electronics today is not turning it on and off and getting hot, but dropping this. And companies like Motorola have pretty severe drop testing. And so that became an important criteria. And one of the things people found, they had pursued SAC 105, which has less silver, and for other reasons, but found it was much better in shock testing. And so this has started what I'll call the proliferation of lead-free alloys, because it looked like everybody was going to focus in on this. And yet when we found this out about 105, SAC 105 being better in drop shock testing, we started investigating this more. And this is some work done by my colleague Ning-Cheng Lee at Indium Corporation. This was the number of drop cycles that tin lead solder would survive, the clear being after it's reflowed, and then the purple being after aging. And aging was pretty gentle, 150 C for 4 days. So you can see SAC 305 is not too good. SAC 105 is better. But what Dr. Lee found was that if you added just tiny amounts, this is essentially SAC 105 with 0.1% manganese, just tiny amounts of other metals, what are now being called dopants by most of us, can dramatically improve some critical properties. And so this is a whole new field in solder science, which is encouraging, but it's created what a lot of us are dreading, and it's the proliferation of alloys. In other words, there was only tin lead solder, pretty much, until lead-free came around, and then we hoped it would be SAC 305, but now there's SAC 305 and 105. Now there's SAC 305 and 105 with dopants in it, and we still haven't converged on it. And so most of us are hoping that we'll be able to converge on a few families of solders for lead-free, but at this point we're still kind of exploding in what we're looking at. So I think that's pretty much all of what I said. So the status of today, I mentioned this doping. Long-term reliability still needs to be established. The other issue that would probably surprise some people in the United States that haven't been experiencing this is exemptees are in a crisis. What do I mean by that? So let's say you don't have to go lead-free because you're making stuff for the military. So you think, great, I'll just use leaded stuff. And it doesn't work, because since essentially almost everything is lead-free in the commercial world, the components that you get are prepared with lead-free finishes. In other words, the little leads on the components used to have tin lead solder, many of them. Now they've got just tin solder, or they've got tin with some other additive. It doesn't have lead in it. And so you can't really get easily leaded components. And so what actually some military people or groups that are very concerned with reliability will buy the components with lead-free finishes on the leads, strip it off, and have it refinished with leaded solder. And so some of my colleagues actually give workshops called Lead-Free for the Exemptee. What people have to do to survive in the world of lead-free if they have an exemption and plan on using lead-free solder. And you know, I would never suggest that military people should use lead-free solder, because many of our military devices are manufactured and sit in a warehouse in Louisiana for 15 years before it goes to war. As amazed as those of us a little older that can remember the technology of the first Gulf War and how impressed we were with cruise missiles and all of that, that was fought in 1991, and the military technology that was implemented, much of it was made in the 70s and sat in warehouse and still has to work. And so the long-term reliability just has not been demonstrated. Okay, I'm going to talk about some of the new material science concerns regarding lead-free solder. One of the things that, even being a material scientist myself, I guess I never thought too much about, and that is that liquid metals are corrosive. You don't tend to think of that too much. But if you have something made of gold and you have a jar of mercury at room temperature, don't put the gold in there. Don't put the silver in there. It can essentially dissolve it. And yet gold is something that we envision as being one of the most corrosion-resistant materials, but not necessarily to metals. Well, stainless steel, which is something we consider to be corrosion-resistant, is strongly attacked by lead-free solder. And one of the thermodynamic aspects of lead-free solder is it's essentially 100% tin, just a little bit of silver and copper, whereas leaded solder was a lot of lead, 37% lead. From a layman's perspective, tin is thermodynamically starved to digest or to dissolve other metals. And so it tends to be more aggressive with copper, which is another problem that I can't go into because of lack of time, but also attacking stainless steel. Well, most of the people that had wave soldering machines were hoping they could take their leaded wave soldering machine, just kind of clean it up and put lead-free solder in it. You really can't do that. You have to have it, either buy a new one or have it retrofitted by the company that makes it to make sure it has the right materials that will resist the lead-free solder. Probably the most explosive issue from a reliability perspective in lead-free electronics is something called tin whiskers. And it's one of these things that if you haven't experienced it before, even if you kind of understand materials, it's kind of shocking almost. And that is that pure tin, or high concentration of tin, something like 90% tin or greater, can often, if it has compressive stresses, will often produce a crystalline growth outside of the tin that looks just like a whisker and can grow literally millimeters. And so here are two electrodes, and here is one tin whisker that's growing and essentially shorting to the next electrode. It can be really pervasive. This is an example of outrageous amounts of tin whiskers. And people can produce it. This is the good news. You know, usually you can control something that you can make really bad and make it better. We can really produce tin whiskers like crazy. And here's an example where it's all over here. And we can make it go away. But the problem is we can't really make it go completely away. And that's what troubles people. So it's caused by compressive stress in the tin. The lead in tin, when we were in an era where these coatings would have lead in them, the lead solid solution strengthens the tin. And even if there is a compressive stress, from a layman's perspective, the tin whisker doesn't start to form because of the strength of the matrix due to the solid solution strengthening of the tin. So in lead-free, this is quite a concern. And one of the mechanisms that makes it worse is, so you have some sort of a lead that's copper and you want to put tin on it. And when you do that, you get a copper-tin intermetallic at the interface between the tin and the copper. But one of the problems is that in absolute sense, the room temperature is more than 50% of the melting temperature of tin. And so at room temperature, tin is still quite active. And once you put this coating on and leave it even at room temperature, the intermetallics continue to slowly form, but it's one directional for the most part. The copper goes in this direction and creates compressive stress here because we have material flowing in. And actually you can get a reduction of copper at this interface, which probably some of you have heard of. They're called Kirkendall voids. And so one of the ways people minimize this is you can put a nickel or silver interface between the tin and the copper, and you'll form a tin nickel intermetallics, and there's nowhere near as much copper diffusion and additional compressive stress creation in the tin. This is an electron micrograph to show how much of the copper can diffuse into the tin. This is the copper is green here, and when we put a nickel layer over it, the nickel being blue, you can see that there's very little up here. This is essentially all tin. So taking action like this minimizes the effect of tin whiskers. But this is enough of a concern that what people have done to show that this doesn't solve the problem is if you then take something like this and put it in a situation where other things can cause stress in the tin, pretty much it's just, if you induce compressive stresses, you might grow tin whiskers. Like literally even just putting a mechanical clamp up here and clamping and pushing down on it could cause tin whiskers to sprout. And thermocycling or something like that. This is some work done by my colleague Dr. Fan at Cookson Electronics. And one of the things that people found is if the tin looks bright, you're in trouble because it probably has higher compressive stresses and a smaller grain size. And this is bright tin, and this is the amount of whiskers they got, something they call the Whisker Index. They took bright tin and they put a little nickel at the interface and got essentially nothing. And here they took some bright tin that had a little bit of bismuth in it, and also which reduced it tremendously from here. But when they used the nickel at the interface, it tremendously reduced it. So there are a lot of strategies for minimizing whisker formation, but and I guess I'll review them before I'll give the summary on this. So if you put the nickel plating on the copper before you put the tin on, if there are ways to induce tensile stress into the compressive stress, that will usually alleviate it. A larger grain size will help. The blue is one that pretty much everybody agrees with. These are some that are still being debated. A thick solder layer. And anything that you can solid solution strengthen the tin with, like bismuth, like maybe 1% bismuth, will help quite a bit. So where is the status of this? Well, and I should mention that in the history of the world, there are 25 verified tin whisker fails. And some of them have been very expensive. Even before lead-free, there are some satellites that somehow had some tin in them that wasn't alloyed with anything, and it caused a tin whisker failure on a satellite, which was like, hundreds of millions of dollars. And you can go on NASA's website, and they have the information on tin whisker fails. So people in the high reliability world really worry about this. I like to point out to these people that I estimate, and you can disagree with me, that this is how many hard drive fails there have been in the world. Does anybody know of anyone who has not experienced a hard drive fail? My family, we're up to about 10. And I've got, had about 15. It's usually the thing that fails. There are all sorts of conferences on tin whiskers, and again, I'm not saying it's a legitimate concern for very high reliability, mission critical products, but typically it takes months for the tin whiskers to grow, and before I'm going to worry about tin whiskers on this, I'm either going to drop it and it's going to have a problem, or we're going to want a newer one. So, but it is probably the thing that material scientists study in lead-free solder that is still contentious, and they have conferences on and so forth. Okay, tin pest. This is tin whiskers is known all over the world. Tin pest is not so commonly known. I guess I should say a little bit about it and then go back. There's a book some of you may have seen that was called Napoleon's Buttons. And, Napoleon had kind of a bad year when he went into Russia, and on the way back, in addition to all the other privations that his soldiers encountered, people said that something called tin pest attacked the tin buttons on their uniforms, and they're starving and freezing and they can't keep their buttons closed, or their coats closed. Almost certainly apocryphal. For one reason, only the officers would have had tin buttons, because tin was and still is almost a precious metal. One of the complaints about going lead-free is lead is cheap, tin is relatively expensive. And others argue that it wasn't that cold, and so on and so forth. Well, what is tin pest? Well, the normal tin that we all know and love that looks pretty and is used, by the way, it's many people call tin jewelry metal. My mind is going blank. The tin and antimony, pewter. Pewter has a lot of tin in it. It's normally body-centered tetragonal, has a density of about 7.3 grams per cubic centimeter, and this is what it is at above 13 degrees C. But an amazing thing happens at below 13 degrees, or I should say can happen at below 13 degrees C, and that is it can go to a different, it takes an allotropic transformation, and it goes to a diamond cubic phase, the alpha phase, and its density drops. Well, that's really bad news, because if it happens, this beautiful piece of tin will start to look like this. That is what is called tin pest. It initially was called Satan's disease. It's not a joke. It's called Satan's disease because pipes in church organs were made of tin. And in the northern European countries, the churches were not heated many years ago. And some of the church organ pipes would end up looking like this. And people declared it was an attack of Satan on the church. And so it was called Satan's disease, or tin plague, or tin disease. The Germans started studying this quite a bit, and they ended up calling it tin plague in German, which is Sinn Pest. And I argue, I don't think anyone else necessarily agrees with me, that because the Germans studied it more than we did in English-speaking countries, they were studying Zinn pest, we started calling it tin pest. So it's really ugly, but one of the good things about it is it's really hard to produce. A lot of scientists have tried to produce it in the lab and failed. And my colleague, Professor Plumbridge over in the UK, has some of the samples that converted, and these are the most shown pictures in the world on tin pest because he's the only guy that's been able to produce any. And that is from virgin material. What will work every time, and this is why people call it a disease, if you take some of this ugly stuff and press it against here and put it in a cold refrigerator, tape it down, it's like it's contagious. It'll spread. And so this is discussed quite a bit, but not too many people have worried about this. I think there'll probably be some cases of it, but it just hasn't generated the concern that tin whiskers has. And this is something I've studied a little more. I've actually written a paper on it, and have been asked to write a summary paper on it. It can occur below 10C, but it's really hard to produce in the lab. And one of the reasons probably is if you have a little bit of antimony or bismuth, its solid solution strengthens the tin, and it can expand to accommodate the needed expansion for the lower density, and so it doesn't readily happen. And when you get tin, when you get solder, you've got contaminant levels of antimony and bismuth and lead, and if they're in the even 0.05%, it can inhibit it. And there's only been one verified case in electronics. Okay, I want to wrap this up. An unfortunate side effect of recycling, you say, how could it be? Well, one of the things that people are designating as the crisis of this era of electronics is counterfeits. Because we're now doing so much more recycling, and because we throw things away so readily, there are all of these type of electronics. To an unscrupulous recycler, you're looking at a gold mine. Each of these components could be sold for $5 to $10, and you got them. Not only did you maybe get them for free, somebody may have paid you $10 to take it. And so what people are doing is they're recycling these, dressing them up, and what they'll do is they'll take the better of them will take a lower grade electronic device, they'll sand the top of it off, and they'll rewrite on here that it was a such and such at 40 megahertz. They'll write that it's a such and such at 100 megahertz, the one that people want today, and they'll relabel it. This is a good one, and this is how good it can be done. This is a fake, this is a counterfeit. Now these are the good guys. At least this one would work, probably, just not as high performance. Some of them, these will actually have something in it that's burned out. And they're as clever enough as these come on, mostly components come on a reel, maybe 1,000 of them, $12 each, $12,000. The first 10 they'll buy from Intel, and they'll be real, genuine parts. And then they'll put the counterfeits at the last 988. And it's a big business, and it's really, really a concern for people where reliability is critical. And one of the things they do, this shows for people that study this, they sand the top of this, but if you look at it under a microscope, this is virgin and this is sanded. Okay, I do want to finish. Many of us believe that there have been waves of innovation throughout history and that we're now into the sustainability wave. And this is one of the things here at Dartmouth. I think we're leaders in studying this. But finally, some people said to me that were kind of upset about all of this. They said, am I safer because of Rojas? And probably not, but these folks are. A study was done by National Geographic in 2007, 6 and 7. This is, and most certainly these people are recycling pre-Rojas products. They published this in January of 2008. You can still get it on their website. This is a young boy in Africa who got a lot of copper wire for free. He can only sell it to the copper vendor if he burns the insulation off, which used to contain carcinogenic materials when it's burned, and now it no longer does. This shows you, this is hopefully being done correctly, recycling. This shows you the extent of the problem. And one of the points I didn't make earlier, the main purpose of Rojas is not that if we do throw something in a landfill, it won't hurt us. That's a secondary purpose. The main purpose is to take lead and these other hazardous materials out of electronics so it's easy and cheap to do recycling. So you don't have to do recycling in a bunny suit with a ventilator on. That was the main purpose to Rojas, to make, because recycling is becoming a fact of life. You can't really recycle easily if lead is in there. But it also protects people today that are in this situation. This man lives, I believe, in India. He's getting free circuit boards. The metal merchant will pay him for this solder. This is almost certainly tin lead solder. He's melting this in a pot that later on he's going to cook supper in. And here is the outside of his humble abode. These are all the circuit boards that he's extracted the solder on in that little pan, and here's tonight's supper. So Rojas is making the world safer today for folks like this, and likely tomorrow for us when recycling becomes more effective life. Thank you for your attention. Questions? Yes.
You didn't say it, but I presume that Rojas components would solder as well to tin lead solder.
That's right. Yeah, Rojas compliant components will not solder as well to tin lead solder. Most people have developed strategies to get it so that it's acceptable, but that is a concern if you have tin lead solder and you're soldering Rojas compliant components.
Through holes, they solder well enough.
Yes. All of it can be accomplished if you work with people to help you optimize your process. And that's kind of one of the things that I often do. Okay?